Hello, my name is Zarkhan, and this is my second lab experiment on the motion of a falling object in Physics 2211. So in this experiment, we're going to be observing the position of a falling object, and so here's some vocabulary. Newton's second law, basically just saying an object's acceleration is dependent on the net force being applied to the object, as well as the mass of the object. Velocity, which is just a function of speed, or the rate at which an object changes its position. Drag is air resistance acting on the object. So in this experiment, air resistance is pushing upwards, and gravity is just the universal force of attraction between all matter. So in this experiment, gravity is pulling the object down towards Earth. And then the main question is, how do outside forces impact the velocity and position of an object as it falls? So the purpose of this experiment is to examine how drag and gravity impact the velocity and position of an object as it falls. And we're going to be comparing our experimental method as well as our two other computational methods. Our experimental method is just our data and tracker, and our first computational method is going to be the data of just gravity acting on the object, and then our second is going to be gravity and drag. So in this experiment, the system is going to be a crumpled piece of paper, and our surroundings is obviously gravity and drag. And so here are just the important formulas we're going to be using, especially in our computational model. Force is equal to mass times acceleration, velocity and position update formula, how we calculate gravity, and how we calculate drag. And FNet we're going to be using in our second computational model, since it has both gravity and drag. And so here's just a diagram showing both gravity and drag force. So first, when an object is let go, it's just gravity, and then through the midway point, drag force starts to act on the object, but gravity is still stronger, and then we reach something called terminal velocity, which is just when drag force and gravity are identical, the same force, equal the same. And so here's my tracker video. And as you can see, when the crumpled piece of paper falls on the ground, there is a downward slope trend. So we observe that there's a downward slope trend as the object falls to the ground. That's what our conclusion is here. And then so this is our computational model, our initial conditions. So left the crumpled piece of paper, the mass as 0.1, and then delta t 1/30 because the number of frames, and then 9.8, and then b for our first computational model is going to be set as 0, since we're only looking at gravity and no air resistance or drag. And so this is our code for gravity. We just set Fnet is equal to j hat times negative mg right here, and then we're also implementing the velocity and position update formulas. So here's the result of that. It's very similar to the tracker trend. And yeah, this is our second computational model, which is gravity and drag. We already calculated or had the code for gravity in the previous computational model, and then we had to add in the F drag, which is now you just use the formula I talked about earlier, and then Fnet is just those two added together, and then B was 0.007. And yeah, we're still using the velocity and position update formulas. And this is the result of that. It's very similar to the gravity computational model graph. And yeah, here's everything together. As you can see, there's some error, especially for the computational ones. For some reason I couldn't find the exact point, so I just did my best, but it's supposed to just be a clean curve. It's not supposed to be up and down. Those are just errors I made. And then the experimental, I guess it differs a lot from the computational, because I probably messed up when I was clicking the average position of the crumpled piece of paper as it was falling through the frame. So that's just my fault. It probably wasn't as precise. But yeah, the same conclusion overall is just a downward slope trend. And then for additional questions, which models, if any, predict a terminal velocity? Terminal velocity is just when drag force and gravity are equal, and the only model that would go with this would be our second computational model, since it has both gravity and drag in it. And I guess, what does it mean for net force? It would be 0 when terminal velocity is happening. And then what if the object was initially thrown downwards? Would terminal velocity be the same or different? I think it would be the same, because again, terminal velocity is just when drag and gravity are equal, so it wouldn't really affect that. But when I'm using my computer models to examine the object velocity as a function of time when it's thrown downwards, the slope is positive, but the terminal velocity would still be the same. Okay, thank you.